soften slowly. Let the noise of the day move further away with each breath. You do not have to listen to every word that follows. The voice will keep going gently. Tonight we are going to drift very slowly into the quiet architecture of the atom, the smallest pieces of matter, where every shift of energy becomes a faint glow of light, and where everything you have ever touched is built from the same patient pieces. This is the Circadian Institute, where each night we travel somewhere ancient and quiet, somewhere too patient for the rush of the day, and let the slow rhythms of the natural world carry our minds toward sleep. Tonight, our destination is the deep, slow story of the atom, the small, bright unit from which every star, every breath, every grain of sand, every drop of water, and every cell of every living thing on Earth is built, with its tiny, dense nucleus, its patient cloud of electrons, the four fundamental forces that hold everything together, and the quiet quantum rules that govern the smallest places in the universe. If you find this calming voice helpful, please subscribe. It is the simplest way to keep these long nights of rest within reach. Tonight, we will travel together into the world of the atom. We will visit the bright, dense nucleus, the patient cloud of electrons that surrounds it, the smaller quarks hidden inside the protons and neutrons, the four fundamental forces that hold every atom together, and the strange, quiet quantum rules that govern the smallest places in the universe. There is no hurry. We have all the time we need. To begin tonight's journey, we will think about what an atom is. An atom is the smallest unit of ordinary matter that still keeps the chemical properties of an element. Every solid object, every drop of liquid, every breath of air, and every living thing you have ever known is built from atoms. They are extraordinarily small, and yet everything large is built from them. An atom is so small that a single drop of water contains roughly 100 sextillion atoms, that is one with 23 zeros after it. If you could line atoms up edge to edge across the head of a small pin, you would need about 1 million of them to span its width. The world we see and touch is built from numbers we can barely imagine. The word atom comes from an ancient Greek word meaning uncuttable. More than 2,000 years ago, the philosopher Democritus suggested that all matter must be made of tiny, indivisible pieces. He was not entirely correct. Atoms can in fact be split apart, but the underlying idea has guided science for centuries since. Every atom has the same basic plan. At the very center is a tiny, dense core called the nucleus. Around the nucleus, in a soft, patient cloud, are the electrons. The nucleus contains nearly all of the mass of the atom, but takes up almost none of its space. The electrons are extraordinarily light, but they fill out the size and shape of the atom around them. If an atom were the size of a sports stadium, the nucleus would be no larger than a pea sitting at the center of the field. The rest of the stadium would be filled very thinly by the electron cloud. Almost everything you think of as solid matter is, in this sense, mostly empty space, held together only by the patient electric forces between charged particles. There are about 92 kinds of atoms found naturally on Earth, and a few dozen more that can be created in laboratories for brief moments. Each kind is called an element. The lightest is hydrogen, with just one proton and one electron. The heaviest natural element is uranium, with 92 protons and many more particles besides. Everything in the universe is built from these elements in different combinations. The number of protons in an atom's nucleus defines which element it is. An atom with 1 proton is hydrogen. An atom with 6 protons is carbon. An atom with 8 protons is oxygen. Add or remove a proton and the entire identity of the atom changes. This single quiet number, deep inside the nucleus, is what makes one substance different from another. Atoms are not solid little balls, despite the way they are often drawn. They are fuzzy quantum structures in which particles do not have exact positions. An electron does not orbit the nucleus the way a planet orbits a star. Instead, it exists as a soft cloud of probability, more dense in some places, less dense in others. This is one of the strangest and most beautiful features of the small world. The first clear evidence that atoms existed came in the early 1900s. Until then, atoms had been a useful idea, but no one had ever observed one directly. Albert Einstein, in 1905, showed that the slow random motion of tiny dust particles in water could only be explained if invisible smaller particles were constantly bumping into them. The bumping particles were atoms. Today, modern microscopes can image individual atoms directly. A scanning tunneling microscope invented in 1981 can map the surface of a metal 1 atom at a time. The resulting images look like soft, round hills arranged in patient geometric patterns. For the first time in human history, we can simply look at the smallest pieces of matter and see them sitting still. Atoms are also extraordinarily stable. Most of the atoms in your body right now were forged inside stars billions of years ago. They have traveled through interstellar space, gathered into clouds, condensed into our solar system, become part of Earth, drifted through countless living things, and eventually found their way into you. They will continue long after the rest of you has gone. The atoms in a single breath of air include some that were once breathed by every human who has ever lived. The carbon in your bones may once have been part of an ancient tree, an ocean creature, or a piece of cosmic dust. The pattern of who is made of what is constantly mixing and remixing, but the atoms themselves remain. Despite their tiny size, atoms behave according to extraordinarily strict and precise rules. The same kind of atom anywhere in the universe, in your body, in a distant star, in a moon of Jupiter, behaves in the same way. The laws that govern atoms are among the most universal and unchanging things in nature. Atoms can join together to form molecules. A water molecule is 2 hydrogen atoms joined to 1 oxygen atom. A carbon dioxide molecule is 1 carbon atom joined to 2 oxygen atoms. The proteins in your body are long chains of thousands of atoms joined in patient, careful patterns. Almost everything around you is some kind of molecule built from a small number of element types. Atoms can also exist alone, especially in very thin gases. The noble gases helium, neon, argon are so chemically inert that their atoms drift through the air as independent units, never joining with anything else. They were among the last elements to be discovered, partly because their chemical invisibility made them so hard to notice. Tonight, the atoms in the air around you are moving constantly. They are bumping into each other gently billions of times every second. They are too small for you to feel, but they are there. The pressure you feel in your ears, the gentle warmth of your skin, the small motion of every breath, all of these are made of atoms quietly going about their patient work. Now, gently, we will look more closely at the nucleus of the atom. the tiny, dense, bright center, where almost all of the mass is held and where the strongest forces in nature are at work. At the very heart of every atom is the nucleus. The nucleus is unimaginably small, about 100,000 times smaller than the atom that surrounds it. Yet despite its tiny size, the nucleus contains more than 99.9% of the mass of the entire atom. Almost everything you weigh is the weight of atomic nuclei. The nucleus is made of two kinds of particles called protons and neutrons. Protons carry a positive electric charge. Neutrons carry no charge at all. They are electrically neutral, which is where their name comes from. Together, protons and neutrons are called nucleons, the particles of the nucleus. A proton and a neutron have almost exactly the same mass, about 1,836 times the mass of an electron. This means that the nucleus, packed with these heavy nucleons, vastly outweighs the lightweight cloud of electrons that surrounds it. The center of an atom is by far its densest place. Protons all carry positive electric charge. Normally, particles with the same charge push each other apart. The protons in a nucleus packed close together ought to fly apart instantly under their own mutual repulsion. The reason they do not is one of the great quiet wonders of nature. A different kind of force called the strong nuclear force holds them together. The strong nuclear force is the most powerful force in nature, but it only acts over extraordinarily short distances, about the size of a nucleus itself. Within this tiny range, it overwhelms the electric repulsion between protons. Outside this range, it vanishes almost completely. The nucleus, in a sense, is the only place in the universe where this force has anything to do. Neutrons help the strong force do its work. By being mixed in among the protons, neutrons add to the strong force binding without adding to the electric repulsion. The result is that heavier nuclei need more neutrons than protons to stay stable. A hydrogen nucleus has 0 or 1 neutron. A uranium nucleus may have well over 140. The number of protons in a nucleus is called the atomic number. The number of protons plus neutrons together is called the mass number. Every atom of a given element has the same atomic number, but different atoms of the same element can have different mass numbers. They have the same number of protons but different numbers of neutrons. These variations are called isotopes. The simplest nucleus belongs to hydrogen. Just a single proton with no neutrons at all. About 99.98% of hydrogen on Earth is this simple form. A tiny fraction has 1 extra neutron, making it the isotope called deuterium. An even tinier fraction has 2 extra neutrons, making the isotope tritium, which is mildly radioactive. Helium has the second simplest nucleus, 2 protons and usually 2 neutrons. This combination is extraordinarily stable. It is so stable that it forms a recognizable unit called the alpha particle, which is emitted from many radioactive nuclei. The fact that helium nuclei are so tightly bound is one reason helium is so common in the universe. As we move up the periodic table, nuclei become more crowded. The heaviest stable nucleus is that of lead, with 82 protons. Beyond lead, all nuclei are at least slightly unstable. They eventually break apart on timescales ranging from fractions of a second to billions of years, The very heavy elements that exist on Earth are slow decaying survivors from the formation of the solar system. Nuclei can also be split apart deliberately. When a heavy uranium nucleus absorbs an extra neutron, it can become unstable and fission into two smaller nuclei, releasing a great deal of energy. This is the process at the heart of nuclear reactors and nuclear weapons. The energy comes from a tiny conversion of mass, exactly as Einstein's famous equation E equals mc squared describes. Nuclei can also be combined. When two light nuclei merge into a heavier one, they too release energy. This is the process called fusion, and it is what powers the Sun and every other star. In the Sun's core, 4 hydrogen nuclei combine through several steps into a single helium nucleus. The energy released as starlight is the difference in mass between the inputs and the outputs. Most of the elements in the universe were forged by fusion inside stars. Hydrogen and a little helium were made in the first few minutes after the Big Bang. Almost everything heavier than helium, the carbon in your body, the oxygen you breathe, the iron in your blood, was built inside the cores of stars and scattered into space when those stars died. The nucleus is held together so tightly that the binding energy per nucleon is enormous. To pull a nucleus apart requires a vast amount of energy, millions of times more particle for particle than is needed to break a chemical bond. This is why nuclear processes can release so much more energy than chemical ones, and why a small amount of nuclear fuel can power a city for a long time. Nuclei occupy almost no space, yet contain almost all of an atom's mass. If you could compress the Earth to nuclear density, keeping all its mass but packing it as tightly as a nucleus, it would fit inside a sphere only a few hundred meters across. The remaining vast bulk of the Earth is, in a real sense, mostly empty space between widely separated little nuclei. Tonight, the nuclei in every atom of your body are sitting quietly at their tiny patient centers. They have been there since long before you were born, and most of them will remain long after you are gone. The slow, steady labor of holding the universe together happens at the centers of atoms, far too small for any eye to see. Now, gently, we will look even more deeply into the inside of the proton and the neutron themselves, where we will find an even smaller and stranger world of particles called quarks. Protons and neutrons are not the smallest pieces of matter. Inside each one are even smaller particles called quarks. Quarks are among the most fundamental particles known. They have no measurable size as far as physics can tell. They may be perfect points with no inner structure at all. Each proton is made of 3 quarks, specifically 2 up quarks and 1 down quark. Each neutron is also made of 3 quarks, but in a different combination, 1 up quark and 2 down quarks. The difference between a proton and a neutron is simply the swap of a single up for a single down. Quarks have fractional electric charges, which is unusual in physics. An up quark has a charge of plus 2/3. A down quark has a charge of minus 1/3. The charges of 2 ups and 1 down add to plus 1, the charge of a proton. The charges of 1 up and 2 downs add to 0, the charge of a neutron. The strangeness of fractional charge is built right into the math. There are 6 types of quarks in total: up, down, charm, strange, top, and bottom. Only up and down quarks are common in stable matter. The other four exist only in high-energy collisions and decay almost instantly back into lighter quarks. Most of the universe is built from just the two lightest types. Quarks are held together inside protons and neutrons by another fundamental force called the strong force, the same strong force that holds nuclei together, though acting in a more direct way at this level. The carriers of the strong force are particles called gluons, and they glue the quarks together so tightly that no quark has ever been observed alone outside of a particle. The strong force has a peculiar behavior. The further apart two quarks are pulled, the stronger the force becomes, the opposite of every familiar force in nature. Trying to separate two quarks is like stretching a stiff spring. Eventually, the spring contains so much energy that new quark-antiquark pairs are created from it, and the energy escapes by making new particles rather than freeing the original quark. This effect is called quark confinement. It is the reason quarks are never seen on their own. They live their entire existence locked inside larger composite particles. Even in the most violent collisions humans have created in particle accelerators, quarks emerge only as parts of new bound states, never alone. Quarks also carry a property called color charge, an unfortunate name because it has nothing to do with visible color. Color charge comes in three varieties, conventionally called red, green, and blue. Within every stable particle, the color charges of the quarks must combine to be color neutral. This is similar to how positive and negative electric charges combine to zero in neutral atoms. Because quarks are held so tightly, a proton or neutron is more than just the sum of its quarks. Most of the mass we measure in a proton is not the mass of the three quarks inside it. It is the energy of the strong force binding them converted to mass by Einstein's equation. The proton is, in a real sense, mostly made of pure binding energy. Quarks were first proposed in 1964 by the physicists Murray Gell-Mann and George Swig, working independently. At first, quarks were treated as a useful mathematical idea rather than real physical objects. It was not until the late 1960s, in deep scattering experiments at the Stanford Linear Accelerator, that direct evidence of point-like particles inside protons was finally found. Today, quarks are central to the standard model of particle physics, the patient mathematical description of all the known fundamental particles and forces. The standard model contains 6 types of quarks, 6 types of leptons, including the electron, and several force-carrying particles. It has been tested with extraordinary precision and has not yet been found to fail. Antiquarks also exist. For every quark, there is a corresponding antiquark with opposite electric charge and opposite color charge. When a quark and an antiquark meet, they annihilate each other in a small burst of energy. The early universe was full of quarks and antiquarks colliding and disappearing. We are made of the small surplus of ordinary quarks that survived. There are also particles called mesons, which are made of one quark and one antiquark joined together. Mesons are unstable and decay quickly, but they appear in cosmic rays and in particle collisions. They were once thought to be the fundamental carriers of the strong force before quarks themselves were discovered. Particles made of 3 quarks together, like protons and neutrons, are called baryons. Most of the ordinary matter in the universe is made of baryons. When astronomers speak of baryonic matter, they mean everything built from quarks bound into protons and neutrons, as opposed to dark matter and dark energy, which are thought to be made of something else entirely. The world inside a proton is restless. The three quarks usually drawn at the heart of the proton are sometimes called the valence quarks. Around them is a constantly shifting sea of additional quark-antiquark pairs and gluons, popping into existence and vanishing again, all within the proton's tiny boundary. The proton, like the atom around it, is more dynamic and more crowded than any simple drawing can show. Tonight, deep inside every proton in every atom of your body, quarks are bound together in their unbreakable trios. The strong force is still patiently holding them. They have never been alone, and they never will be. The smallest building blocks of matter live their entire lives in quiet, committed company. Now gently, we will move outward from the nucleus and visit the soft, patient cloud of electrons that surrounds it, the lightweight particles that give atoms their size and shape and their personality in chemistry. Surrounding every atomic nucleus is a cloud of electrons. Electrons are extraordinarily light, almost 2,000 times lighter than a proton or a neutron, but they are the part of the atom that the outside world actually touches. Whenever two pieces of matter come into contact, it is their outer electrons that meet first. The electron carries a negative electric charge, exactly opposite in size to the positive charge of a proton. In a neutral atom, the number of electrons matches the number of protons, and the total charge of the atom is zero. If an atom gains or loses an electron, it becomes electrically charged, and we call it an ion. Electrons do not orbit the nucleus like planets around a star. Instead, they exist as fuzzy quantum clouds of probability. An electron has no exact position. It is described by a wave function that gives the chance of finding it in different places. The shape of this cloud depends on the electron's energy and which kind of orbital it is in. Electron orbitals come in different shapes. The simplest orbital, called the s orbital, is a soft spherical cloud centered on the nucleus. Other orbitals, called p, d, and f, have lobed or petal-like shapes. The overall structure of the electron cloud in any atom is built from these different orbital shapes layered around the center. Electrons fill their orbitals in a specific order, starting from the lowest energy and working up. Each orbital can hold at most 2 electrons, which must have opposite quantum spin. This rule, called the Pauli exclusion principle, is one of the great organizing laws of nature. Without it, all electrons would crowd into the lowest level, and atoms as we know them would not exist. Each electron also has a property called spin, which behaves like a tiny intrinsic angular momentum. Spin can take only 2 values, up or down. The Pauli exclusion principle means that 2 electrons in the same orbital must have opposite spins. This simple pairing rule shapes nearly all of chemistry. The outermost electrons of an atom are called valence electrons. They are the ones involved in chemistry, in forming bonds with other atoms, in conducting electricity, and producing the colors we see. 2 atoms with the same number of valence electrons usually behave in similar chemical ways, which is why the periodic table is grouped into columns of related elements. Electrons can move between orbitals if they absorb or release energy. When an electron drops from a higher orbital to a lower one, it gives up energy in the form of a photon, a tiny packet of light. When it absorbs a photon of just the right energy, it can jump up to a higher orbital. This is how atoms emit and absorb light. The colors we see all around us come from electron transitions in atoms and molecules. The red of a rose, the green of a leaf, the blue of the sky, all are produced by electrons absorbing some wavelengths of light and reflecting or transmitting others. The visible world is, in a sense, a vast, slow conversation between sunlight and electrons. Electrons can also be removed from atoms entirely, leaving behind positive ions. When ultraviolet light, X-rays, or fast-moving particles strike atoms, they can knock electrons free. The freed electrons can then carry electric current, react chemically, or be detected as signals. The ability to free and direct electrons is the basis of all modern electronics. Electric current is, at its heart, the patient flow of electrons through a material in a copper wire carrying current. Electrons drift slowly from one end to the other, jumping from atom to atom. The lights in your home, the screen you may have read on tonight, the heartbeat monitored in a hospital, all are guided by these patient streams of electrons. Electrons were the first subatomic particles ever discovered. In 1897, the British physicist J.J. Thomson showed that the mysterious cathode rays produced in vacuum tubes were actually streams of tiny, negatively charged particles. The particles were vastly smaller than any atom. They were named electrons soon after. The electron is one of the most precisely measured objects in all of science. Its mass, its charge, its magnetic moment, and its behavior in electric and magnetic fields have all been determined to extraordinary accuracy. The agreement between theory and measurement for the electron is one of the great quiet triumphs of physics. Electrons are believed to be truly fundamental. They have no measurable size, no internal structure, and no smaller particles inside them. As far as physics knows, electrons are simple points of mass and charge with a quantum behavior. The same kind of electron is found in every atom in the universe. Despite being point-like, electrons can exhibit wave behavior. In the famous double-slit experiment, electrons fired one at a time through two slits gradually build up an interference pattern, as though each electron passes through both slits at once. This is one of the strangest results in all of physics, and it has been confirmed countless times. Tonight, the electrons in every atom of your body are filling their patient orbitals exactly as they have since you were born. They are constantly absorbing and emitting tiny amounts of light, reacting to fields, sharing themselves between atoms in chemical bonds. They never tire, they never stop. They are the part of you that has always been in this small, quiet sense, conversing with the universe. Now, gently, we will look more carefully at the structure of these orbitals, at the patient rules that determine where electrons live, and at the energy levels that give atoms their distinct chemistry. Around every atomic nucleus, electrons arrange themselves into shells of different energies. These shells are not solid layers but groups of orbitals at similar energy levels. The shells are numbered outward from the nucleus, starting at 1. The first shell holds at most 2 electrons, the second up to 8, the third up to 18, and so on. Within each shell there are subshells named S, P, D, and F. Each subshell consists of one or more orbitals of identical energy. The S subshell has 1 orbital, the P has 3, the D has 5, the F has 7. Each orbital holds at most 2 electrons, so the total capacity grows quickly as we move outward. The energy levels of orbitals follow a patient pattern. Lower shells fill first, but the order is not strictly outward. Some lower energy orbitals in outer shells fill before higher energy orbitals in inner shells. This subtle order is captured in a chart called the Aufbau principle, named from the German word for building up. Hund's rule adds another touch of patience to orbital filling. When several orbitals of the same energy are available, electrons spread out across them singly before pairing up. This minimizes electron-electron repulsion. The result is that atoms with partially filled subshells often have several unpaired electrons, which gives them magnetic and chemical properties. Energy levels are quantized. They are not continuous. An electron can only have certain allowed energies, never values in between. When the electron changes energy, it must take or release the exact difference, no more and no less. This quantization is one of the most fundamental discoveries of the early 20th century. The lowest energy state of an atom is called its ground state. When all electrons sit in the lowest available orbitals consistent with the rules, the atom is at rest in the deepest, calmest configuration possible. Most atoms in everyday matter are in their ground state most of the time. They are, in a sense, gently asleep. When an atom absorbs energy from light, from heat, from a collision, one of its electrons can jump to a higher orbital. The atom is then said to be in an excited state. Excited states are usually unstable after a short time. The electron drops back down and the absorbed energy is released often as a photon of light. The colors of fireworks come from electron transitions. Different metal salts in fireworks each produce different colors when their atoms are heated. Strontium gives red, barium gives green, copper gives blue, sodium gives yellow. Each color is the signature of a specific electron transition in a specific element. The orbital pattern of an atom determines almost everything about its chemistry. Atoms with completely filled outer shells, like the noble gases, are nearly inert. They have no extra electrons to share and no empty spots to fill. Atoms with partially filled outer shells are reactive. They share, give up, or accept electrons to reach more stable arrangements. The reason the periodic table has the shape it does, 18 columns, several rows of decreasing length, is the order in which orbitals fill. Elements in the same column have similar valence electron configurations, which gives them similar chemical behavior. The geometry of the table is deep down a portrait of orbital filling. Hydrogen and helium fill the first shell. Lithium through neon fill the second. Sodium through argon fill the third. As we move down the table, the size of an atom grows. Cesium, with electrons spread across 6 shells, is one of the largest atoms found in nature. Helium, with all its electrons in the first shell, is one of the smallest. The energy needed to remove an electron from an atom is called the ionization energy. Atoms with full outer shells have very high ionization energies. They hold their electrons tightly. Atoms with a single outer electron, like sodium or potassium, have very low ionization energies. This difference is the basis of much of chemistry. Electron affinity is the opposite. The energy released when an atom gains an extra electron. Atoms missing only one electron from a full outer shell, like chlorine or fluorine, have very high electron affinities. They eagerly accept incoming electrons. The combination of high electron affinity in one atom and low ionization energy in another is what creates the strongest ionic bond. The actual shapes of orbitals are stranger and more beautiful than any simple drawing can show. Some look like soft spheres, some look like a pair of teardrops touching at the nucleus, some look like four-lobed cloverleafs. Higher energy orbitals can be even more elaborate. They are mathematical functions made visible. Despite their complexity, the orbitals of every atom in the universe follow the same patient quantum rules. The same energy level diagram drawn for a single hydrogen atom in a chemistry textbook describes hydrogen atoms inside stars billions of light years away. The deep laws of the small are perfectly universal. Tonight, the orbitals in every atom around you are softly filled in exactly the right places. The electrons in your fingertips are sitting in their proper energy levels. The electrons in the air you are breathing are doing the same. Even the electrons in stars and distant galaxies are doing the same. The pattern is universal, quiet, patient. Now, gently, we will step back and look at how the order of orbital filling produces the entire periodic table, the great patient family portrait of every element in the universe. The periodic table is one of the most beautiful patterns ever discovered in nature. In a single chart, it organizes every chemical element by the number of protons in its nucleus and groups elements with similar properties into the same vertical columns. The structure of the table is, in fact, a direct picture of how electrons fill their orbitals. The first person to publish a recognizable periodic table was the Russian chemist Dmitry Mendeleev in 1869. Mendeleev arranged the known elements by atomic weight and noticed that similar properties recurred at regular intervals. He even left gaps for elements that had not yet been discovered, predicting their properties from the pattern. Several of these predictions were soon confirmed. Today's periodic table is organized by atomic number rather than atomic weight. The rows are called periods and the columns are called groups. There are 7 periods and 18 groups. 2 long rows of lanthanides and actinides are usually drawn below the main body of the table, where they would otherwise stretch it sideways too far. Group 1 on the far left contains the alkali metals, lithium, sodium, potassium, and others. They are soft, shiny metals that react vigorously with water. They each have a single electron in their outermost shell, which they readily give up to form positive ions. Their chemistry is dominated by this lone outer electron. Group 2 contains the alkaline earth metals, including beryllium, magnesium, calcium, and others. They have 2 outer electrons. They are slightly less reactive than the Group 1 metals, but still readily form positive ions. Calcium, important for bones and shells, is among the most common elements in living things. On the far right of the table sit the noble gases: helium, neon, argon, krypton, xenon, and radon. Each one has a completely filled outer shell, which makes them remarkably stable and chemically inert. They were among the last elements to be discovered because their lack of reactivity made them nearly invisible to chemistry. Just to the left of the noble gases are the halogens: fluorine, chlorine, bromine, iodine. They are missing a single electron from a full outer shell, which makes them extremely eager to gain one. They are among the most reactive nonmetals on the table. Chlorine, when combined with sodium, forms ordinary table salt. In the middle of the table sit the transition metals: iron, copper, silver, gold, platinum, and many more. They have partially filled inner d orbitals, which gives them complex chemistry. They form bright, colorful compounds, conduct electricity well, and play essential roles in living things through enzymes that contain transition metal atoms at their centers. The lanthanides, sometimes called the rare earth elements, are 15 related elements with similar chemistry. They are not actually rare, but they are difficult to separate from each other because they behave so similarly. Several are used in modern technology, in magnets, in screens, and in batteries. The actinides include uranium, thorium, and plutonium, along with many short-lived heavier elements that exist only in laboratories. Many of the actinides are radioactive. Some, like uranium, are common enough on Earth to be mined. Others have been created only by carefully smashing atoms together inside particle accelerators. The lightest element, hydrogen, sits awkwardly in the periodic table. It has a single electron, like the alkali metals, but it is a colorless gas rather than a shiny metal. Some periodic tables place it in group 1, some treat it as its own category. Its simple nature gives it a kind of independence within the rest of the table. The heaviest naturally occurring element is uranium, with 92 protons. Beyond uranium are the transuranic elements, which were all first created in laboratories. Some have been named for famous physicists: Einsteinium, fermium, Mendelevium, Oppenheimer-related elements, and others for places where they were first synthesized. Many elements are essential for life. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur make up most of the organic molecules in your body. Sodium and potassium carry the electrical signals in your nerves. Calcium hardens your bones. Iron carries oxygen in your blood. Trace amounts of zinc, magnesium, copper, and others run essential reactions inside your cells. The most abundant element in the universe is hydrogen, which makes up roughly 75% of all ordinary matter. Helium accounts for most of the rest. All the heavier elements combined, every atom of every other element ever, add up to only a few percent of the total. The cosmos is overwhelmingly built from the two lightest elements. The most abundant element in the Earth's crust is oxygen, which makes up nearly half its mass. Silicon is next, then aluminum, then iron. The Earth itself, taken as a whole, contains much more iron and silicon than the crust does. Most of the iron has sunk into the planet's core, where it forms the inner sphere whose motion generates Earth's magnetic field. Tonight, every element in the periodic table exists somewhere, most of them in distant stars or interstellar clouds. some of them in the earth around you, many of them in your own body. The patient family of elements is everywhere at once. There is nothing in the visible universe that is not a member of this quiet family. Now, gently, we will look at how atoms join with one another to form everything we see. We will visit the patient world of chemical bonds. Atoms rarely live alone. Almost everything in the world around you is made of molecules, groups of atoms joined by chemical bonds. Bonds form when atoms can lower their total energy by sharing or transferring electrons with one another. The patient pattern of which atoms can bond with which and in what numbers is the basis of all chemistry. There are several main types of chemical bond. The two most important are ionic bonds, in which one atom gives up electrons to another, and covalent bonds, in which atoms share electrons between them. A third type, the metallic bond, occurs in metals, where many atoms share a vast common cloud of electrons. In an ionic bond, one atom transfers an electron entirely to another. The atom that loses the electron becomes a positive ion. The atom that gains it becomes a negative ion. The two oppositely charged ions then attract each other and stick together. Table salt, sodium chloride, is formed exactly this way. Sodium gives up an electron and chlorine accepts it. Ionic compounds typically form crystals, patient, regular arrangements of alternating positive and negative ions. Salt crystals, for example, are little cubic stacks of sodium and chloride ions, repeating the same pattern again and again. The same pattern that gives a grain of salt its sharp corners gives a vast salt mine its quiet geometry. In a covalent bond, two atoms share a pair of electrons rather than transferring them. The shared electrons spend time near both nuclei, holding the atoms together. Many of the molecules of life are built from covalent bonds. The bonds between carbon, hydrogen, oxygen, and nitrogen in proteins, sugars, fats, and DNA are all covalent. Covalent bonds can be single, double, or triple, depending on how many electron pairs are shared. A double bond is twice as strong as a single bond, and a triple bond is even stronger. Carbon with 4 outer electrons is famously good at forming bonds of various strengths with many different partners, which is why it sits at the heart of organic chemistry and life. Water, the most common molecule on the surface of the Earth, has 2 covalent bonds, one oxygen atom bonded to 2 hydrogen atoms. The bonds form at a soft angle of about 104 degrees. This bent shape gives the water molecule its slight electric polarity, which in turn gives water its many remarkable properties. Hydrogen bonds are a weaker kind of attraction. They occur between a hydrogen atom in one molecule and an electron-rich atom in another. Hydrogen bonds are much weaker than covalent bonds, but they are extremely common. Water molecules cling to each other through hydrogen bonds. DNA strands are held together in pairs by hydrogen bonds. In metals, the outer electrons of every atom are shared in a vast common cloud, which can drift freely throughout the metal. This is what makes metals shiny, malleable, and electrically conductive. When you press a metal, the underlying atoms can slide past each other without breaking apart because the electron sea moves with them. Some atoms form bonds with one another at very strange angles. Pure carbon, in the form of diamond, has each atom bonded to 4 neighbors in a tetrahedral arrangement. This makes diamond the hardest natural substance known. The same carbon atoms arranged in flat layered sheets instead form graphite, the soft, slippery material in pencil lead. The strength of a chemical bond is measured in how much energy is needed to break it. Most chemical bonds are millions of times weaker than the nuclear forces holding the nucleus together. Yet the patient pattern of chemical bonds, every bond formed, every bond broken, is what shapes nearly all of everyday matter. Chemical reactions are patient processes in which old bonds break and new ones form. The atoms involved are conserved. None is created or destroyed in a chemical reaction. They simply rearrange themselves into different combinations. The slow burning of wood, the slow rusting of iron, the swift firing of a neuron in the brain, all are atoms quietly rearranging. The shape of a molecule depends on how its bonds are arranged in 3 dimensions. Proteins fold themselves into intricate shapes, with the shape determining their function. DNA twists into its famous double helix. Enzymes are shaped to fit perfectly with the molecules they act upon. Molecular shape is, in a real sense, molecular meaning. Many molecules also have a left-handed and a right-handed form called enantiomers. The two are mirror images of each other, like a pair of hands. Most biological molecules exist as only one of the 2 forms. This consistent handedness of life is one of the deep, quiet mysteries of how biology came to be. Chemical bonds also store energy. When wood burns, the energy released as heat comes from rearranging bonds in cellulose and oxygen into new, lower energy bonds in carbon dioxide and water. When your body digests food, it slowly breaks bonds in carbohydrates and uses the released energy to power your cells. Energy flows through the world by way of bonds being made and broken. Tonight, in every cell of your body, countless chemical bonds are being made and broken. The atoms are not being destroyed, they are simply finding new partners in patient sequence. The slow biology of being alive is, at the bottom, the slow geometry of atoms holding hands and letting go. Now, gently, we will return to the nucleus and look at what happens when it is not perfectly stable. We will visit the patient world of isotopes and radioactive decay. Every element comes in several forms, called isotopes. Isotopes of the same element all have the same number of protons in their nucleus, but different numbers of neutrons. Hydrogen, for example, has 3 natural isotopes: ordinary hydrogen with no neutrons, deuterium with 1 neutron, and tritium with 2. Each isotope has slightly different physical properties but identical chemistry. Many isotopes are stable. They sit at the center of their atoms indefinitely without changing. Carbon-12, oxygen-16, and iron-56 are examples of stable nuclei. They are the same now as they were billions of years ago, and they will remain the same for the rest of cosmic history. Other isotopes are unstable. They are slightly out of balance, too many neutrons or too many protons or too much energy, and at some patient pace they rearrange themselves into more stable forms. This rearrangement is called radioactive decay. The element changes and the energy released travels outward as radiation. There are several common kinds of radioactive decay. In alpha decay, a heavy nucleus ejects an alpha particle, a tight cluster of 2 protons and 2 neutrons identical to a helium nucleus. The original element loses 2 protons and turns into a different element entirely. Uranium decaying to thorium is an example of alpha decay. In beta decay, a neutron transforms into a proton, or a proton into a neutron, with the emission of a small particle called a beta particle and another particle called a neutrino. The atom changes from one element to the next on the periodic table. Beta decay is the most common form of decay for unstable nuclei that have a slight excess of neutrons or protons. In gamma decay, the nucleus does not change which element it is, but it sheds excess energy by emitting a high-energy photon called a gamma ray. Gamma rays are the most energetic form of light. Gamma decay often follows alpha or beta decay as the new nucleus settles into its lowest energy form. Each radioactive isotope has a characteristic time called its half-life. The half-life is the time it takes for half of a sample to decay. Half-lives vary enormously. Uranium-238 has a half-life of about 4.5 billion years, nearly the age of the Earth. Carbon-14 has a half-life of about 5,700 years. Some isotopes have half-lives of less than a billionth of a second. Radioactive decay is a probabilistic process for any single nucleus. We cannot say exactly when it will decay. We can only say what its chance of decaying within a given time is, but for a large number of nuclei, the average behavior is extraordinarily predictable. This is one of the strange, beautiful features of quantum behavior at the nuclear scale. The natural radioactivity of certain isotopes was discovered in 1896 by Henri Becquerel, who found that uranium salts gave off mysterious rays that fogged photographic plates. Marie and Pierre Curie soon followed up his work and discovered new radioactive elements, including polonium and radium. The discovery of radioactivity opened up a new chapter of physics. Radioactivity is the source of much of the natural heat in the Earth. Long-lived radioactive isotopes of uranium, thorium, and potassium scattered throughout the planet's interior decay, slowly over billions of years, releasing heat. This radioactive heat helps drive the slow motion of tectonic plates, the rising of magma, and the patient working of the planet itself. Radioactive isotopes are used in many beneficial ways. Carbon dating uses the slow decay of carbon-14 to determine the age of organic remains up to 50,000 years old. Medical imaging uses short-lived isotopes injected into the body to map blood flow and metabolism. Cancer therapy uses focused radiation to selectively destroy diseased cells. Radioactive isotopes are also used in scientific instruments. The smoke detectors in many homes contain a tiny amount of americium-241, an artificially made radioactive isotope. When smoke disrupts the patient flow of alpha particles in the detector, an alarm is triggered. Atomic physics watches quietly over your nights. Many of the heavier elements on Earth today are slow-decaying survivors from the time when our planet formed. Uranium-235 and uranium-238 have been gradually decaying ever since they were created in a long-ago supernova. The very atoms in your bones may include trace amounts of these ancient elements, still quietly losing themselves to time. The very high stability of certain nuclei is the reason that some elements are very common and others are very rare. Iron 56 has the highest binding energy per nucleon of any common nucleus, which makes it especially stable. As a result, iron is one of the more abundant heavy elements in the universe and in the cores of dead stars. There are also a few extremely rare and short-lived isotopes that can only be made in particle accelerators. Some live for less than 1,000th of a second before decaying into something else. Physicists study these fleeting nuclei to learn about the patient rules that govern how nuclei are held together at the edge of their existence. Tonight, throughout the earth around you, throughout your own body, a small, steady drumbeat of radioactive decay is patiently going on. A few atoms in every gram of every substance are slowly losing themselves to time and turning into other elements. This patient, quiet conversion has been going on for billions of years. Now, gently, we will step back from the nucleus and look at the four fundamental forces of nature, the patient, invisible rules that hold every atom and every star in place. All of the interactions in the physical universe can be traced to just four fundamental forces. They are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Every other force you can think of, friction, tension in a rope, the wind in your face, the firing of a neuron, is some combination of these four working together at different scales. Gravity is the weakest of the four forces, but it has unlimited range and is always attractive. Every piece of matter pulls on every other piece of matter by an amount that depends on their masses and the distance between them. The reason gravity dominates at large scales is that it never cancels out. There is no negative gravity to oppose ordinary gravity. Gravity holds the moon in orbit around the Earth. It holds the Earth in orbit around the Sun. It binds the Sun and billions of other stars into the Milky Way galaxy. It guides the slow, patient turning of galaxies through cosmic time. Every cosmic structure larger than a planet is shaped by gravity, even though at the smallest scales, gravity is almost too weak to detect. Electromagnetism is much stronger than gravity, but it can be both attractive and repulsive. Like charges repel each other, opposite charges attract. The electromagnetic force binds electrons to atomic nuclei, holds molecules together, drives chemistry, and produces all of the light we see. Almost everything you experience in everyday life is electromagnetic in origin. Electromagnetism also includes magnetism. A moving electric charge produces a magnetic field, and a changing magnetic field induces an electric current. The unification of electricity and magnetism was one of the great triumphs of 19th century physics, accomplished by James Clerk Maxwell in a set of beautifully concise equations. Light itself is an electromagnetic phenomenon. A wave of changing electric and magnetic fields traveling together through space is exactly what we call light. The color of light corresponds to its wavelength. Visible light occupies just a narrow slice of a much wider spectrum, which also includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. The strong nuclear force, as we have heard, holds quarks together inside protons and neutrons, and holds nucleons together inside atomic nuclei. It is by far the strongest of the four forces, but only acts over very short distances about the size of a nucleus. Outside this tiny range, the strong force essentially vanishes. The weak nuclear force is harder to picture, but no less essential. It governs certain kinds of radioactive decay, particularly the beta decay in which a neutron transforms into a proton. It is responsible for setting the slow pace of fusion in the Sun. Without the weak force, stars could not shine for billions of years. They would burn through their hydrogen far too fast. Each fundamental force has its own carriers. The carriers of electromagnetism are photons. The carriers of the strong force are gluons. The carriers of the weak force are W and Z bosons. The hypothetical carrier of gravity is called the graviton, though it has never been directly detected. These force carrier particles are exchanged between matter particles to transmit the forces. In the 1960s, physicists discovered that the electromagnetic and weak forces are actually two different aspects of a single, more fundamental force called the electroweak force at very high energies, like those present in the very early universe. The two forces blend together. As the universe cooled, they separated into the distinct forces we now observe. Physicists have long hoped to unify the strong force and the electroweak force as well, into what is sometimes called a grand unified theory. Some progress has been made, but no fully complete grand unified theory has yet been confirmed. The patient work of looking for one continues in laboratories and observatories around the world. Gravity remains the great outlier. Despite a century of effort, no satisfying quantum theory of gravity has yet been found. General relativity describes gravity beautifully on large scales, and quantum mechanics describes the other three forces beautifully on small scales, but the two have not been combined into a single consistent theory. This is one of the deepest open questions of physics. Each of the four forces has its own characteristic strength and range. The strong force is about 100 times stronger than electromagnetism, but only acts over nuclear distances. Electromagnetism reaches across the universe, but cancels itself in neutral matter. The weak force is much weaker than electromagnetism and acts only over distances smaller than a proton. Gravity is by far the weakest, but it is the boss of cosmic scales. The fundamental forces shape the structure of matter at every scale. At the smallest scale, the strong force binds quarks into protons and neutrons. At the nuclear scale, the strong and weak forces shape atomic nuclei. At the atomic and molecular scale, electromagnetism shapes atoms and bonds. At the cosmic scale, gravity shapes planets, stars, and galaxies. If any of the fundamental forces were even slightly different in strength, the universe would be a very different place. If gravity were a little stronger, stars would burn out too quickly for life to evolve. If the strong force were a little weaker, atomic nuclei would not be stable. The precise values of the forces seem, in some quiet sense, to be tuned for the existence of things like us. Tonight, all four fundamental forces are at work in every atom of your body. Gravity is holding you to the earth. Electromagnetism is holding your atoms together and producing every signal in your nerves. The strong force is holding the protons and neutrons in every cell of you in their patient places. The weak force is quietly running its slow occasional reactions in distant cells. They are always present. Now gently, we will look more closely at one of these forces, electromagnetism, and at how it produces the light we see and the charge we feel. Electromagnetism is the most familiar of the fundamental forces. Almost every interaction in everyday life, touch, friction, light, color, sound through air, the working of any machine comes from electromagnetism. The force acts between charged particles, and it has both electric and magnetic faces which are deeply intertwined. Electric charge comes in two kinds, positive and negative. Like charges repel, and unlike charges attract. Charge is conserved, it can be moved from one place to another but never created or destroyed. The total electric charge of the universe is believed to be zero, with positive and negative charges balanced in vast quiet symmetry. Static electricity is one of the simplest manifestations of the electromagnetic force. When you rub a balloon on your hair, you transfer a small number of electrons from your hair to the balloon. The balloon becomes negatively charged and your hair becomes positively charged. They then attract each other gently until the charges find a way to flow back together. Lightning is a vast version of the same phenomenon. In a thunderstorm, charges gradually separate within tall clouds. Eventually, the difference between charges becomes so large that the air can no longer hold them apart. The charges leap across the gap in a sudden bright discharge, briefly heating the air to temperatures hotter than the surface of the sun. Magnetism is the other half of electromagnetism. A bar magnet has a north pole and a south pole. Like poles repel, and opposite poles attract, magnetism is produced by moving electric charges, most famously by electrons in atoms with unpaired spins. Iron is strongly magnetic because its inner electron arrangement leaves many unpaired spins aligned together. Earth itself is a giant magnet. Its molten iron core, slowly stirring as the planet rotates, generates a vast magnetic field that surrounds the planet. This magnetic field is what makes compasses point north and south. It also shields Earth's atmosphere from the steady stream of charged particles flowing out from the sun. Light is a traveling wave of electromagnetic field. As an electric field oscillates, it produces a changing magnetic field, which in turn produces a changing electric field, and so on. The wave travels through empty space at the speed of light, about 300,000 kilometers per second, the fastest speed in the universe. Light comes in tiny packets called photons. Each photon carries a specific amount of energy that depends on the wavelength of the light. Red light has lower energy photons. Blue light has higher energy photons. Ultraviolet, X-rays, and gamma rays have even higher energy photons, which is why they can ionize atoms and cause damage to living tissue. The visible spectrum, the light our eyes can detect, extends from about 400 to 700 nanometers in wavelength. Red is at the long end, violet at the short. Beyond visible light in each direction are vast ranges of invisible electromagnetic radiation. Radio waves can be many meters long. Gamma rays can be smaller than an atomic nucleus. The color of any object you see is the result of which wavelengths of light its atoms and molecules absorb and which they reflect or emit. A green leaf appears green because chlorophyll molecules absorb red and blue light strongly while reflecting green. A red flower reflects red and absorbs other colors, white paper reflects all colors equally, black paper absorbs them all. Atoms can also emit light. When an excited electron drops back to a lower orbital, it releases a photon with exactly the energy difference between the two levels. Each atom has its own characteristic set of allowed energies, so the photons it emits have characteristic wavelengths. The light from a neon sign, a sodium street lamp, or a distant star carries a fingerprint of which atoms produced it. Electric currents are streams of charged particles. In metals, the carriers are electrons. In ionic solutions, like the salty water inside cells, the carriers are positive and negative ions. In a plasma, like the gas of the sun, ions and electrons flow freely past each other. The flow of electric charge through a circuit is what powers nearly all of modern technology. The unification of electricity, magnetism, and light into a single theory by James Clerk Maxwell in the 1860s was one of the great triumphs of physics. Maxwell's equations describe electromagnetic phenomena across an enormous range of scales, from the smallest radio waves to the brightest gamma rays. His equations remain in daily use today, more than a century and a half later. Quantum electrodynamics, developed in the 1940s, replaces Maxwell's classical theory at the smallest scales. In quantum electrodynamics, every electromagnetic interaction is mediated by the exchange of photons. The theory has been tested with extraordinary precision and is in agreement with measurement to many decimal places. It is one of the most successful scientific theories ever developed. Electromagnetism gives the world its texture. The hardness of a stone, the softness of cloth, the slipperiness of water, the resistance of air, all are subtle expressions of electromagnetic forces between atoms and molecules. Two objects pressing against each other never actually touch in any final sense. They are merely held apart by the electromagnetic repulsion of their outer electron. Tonight, electromagnetism is at work in everything you can see, hear, touch, or imagine. The very light that travels from these words into your eyes is an electromagnetic wave. The signal moving along your optic nerve is an electromagnetic disturbance. The chemistry of every dreaming cell in your brain is held together by electromagnetic bonds. Now gently, we will look at the deepest layer of all, at the quantum behavior of atoms, where things at the smallest scale are stranger and softer than common sense would ever guess. At the smallest scales of matter, the familiar everyday rules of motion no longer apply. Atoms, electrons, photons, and other tiny particles behave according to a different set of rules called quantum mechanics. The quantum world is strange, beautiful, and remarkably consistent with itself, even when it does not match our intuitions. One of the central principles of quantum mechanics is the Heisenberg uncertainty principle. It states that we cannot simultaneously know the exact position and the exact momentum of a particle. The more precisely we measure one, the less precisely we can know the other. This is not a problem of measurement. It is a fundamental feature of the universe. In the quantum world, particles do not have definite positions until they are measured. Before measurement, an electron exists as a spread-out wave of possibilities. The wave tells us where the electron is likely to be found if we look. The act of looking gives the electron a position, but until then, its location is undefined in a deep philosophical sense. Quantum particles can also be in two states at once. An electron can be spinning up and spinning down at the same time in a state called a superposition. It only chooses one or the other when measured. This sounds strange, but it has been confirmed countless times in experiment. It is the basis for the new technology of quantum computing. Quantum particles can also be entangled. Two particles that have interacted in the right way can have their properties linked, even after they are separated by long distances. Measuring one immediately determines the other's state. This eerie connection, called entanglement, was once called spooky action at a distance by Einstein. It has now been experimentally demonstrated many times. Quantum tunneling is another strange phenomenon. Sometimes a particle can pass through an energy barrier that, classically, it should not have enough energy to cross. The particle's wave function extends slightly beyond the barrier, and so the particle has a small chance of appearing on the far side. Quantum tunneling is essential to nuclear fusion in stars and to the workings of certain electronic devices. Quantum behavior is governed by a mathematical object called the wave function. The wave function encodes all information about a particle or system. Its evolution in time is described by the Schrödinger equation, named for the Austrian physicist who wrote it down in 1926. The equation is one of the foundational tools of modern physics. Quantum mechanics arose in the early 20th century to explain a number of strange experimental results. In 1900, Max Planck found that he could explain the spectrum of light emitted by hot objects only by assuming that energy was exchanged in discrete packets. Albert Einstein then showed that light itself comes in such packets. Niels Bohr applied the idea to atoms in 1913. Quantum mechanics is one of the most accurately tested theories in all of science. Every measurement of every quantum prediction made over the last 100 years has confirmed it. There is no known physical experiment that contradicts quantum mechanics. Its strangeness is not a sign of error. It is a sign of how unfamiliar the small world is compared to the world of our senses. At human scales, quantum effects average out, and we see the familiar classical world. A baseball does not visibly exist in a superposition of positions. A car does not tunnel through a wall. Quantum behavior is hidden at our scale by the enormous numbers of atoms involved. The quantum world is real, but mostly invisible to direct human experience. Yet quantum effects can sometimes become visible at human scales. Lasers, superconductors, transistors, fluorescent lights, atomic clocks, and quantum dots all rely on quantum behavior to function. Modern medicine, communication, and computing all depend, deep down, on the patient strange rules of the quantum world. Quantum mechanics also tells us something about emptiness. The vacuum of space is not truly empty. Pairs of particles and antiparticles constantly appear and disappear, borrowed briefly from the energy of the vacuum and quickly returned. This restless quantum activity has measurable effects, including the subtle Casimir force between two close parallel plates of metal. The quantum vacuum may even hold the explanation for dark energy, the mysterious form of energy that seems to be accelerating the expansion of the universe. Some physicists believe dark energy may be the energy of the vacuum itself, though the predicted value disagrees with the observed value by many orders of magnitude. The mystery is not yet solved. Quantum biology is a newer field that studies whether quantum effects play important roles in living systems. There is good evidence that photosynthesis uses quantum coherence to efficiently transport energy in plants. Some bird species may rely on quantum entanglement in their eyes to sense the Earth's magnetic field. Life itself may use quantum tricks in ways we are only beginning to discover. The deeper philosophical questions about quantum mechanics, what the wave function really is, what happens during measurement, whether other branches of reality exist, remain open. Different interpretations exist, including the Copenhagen interpretation, the many worlds interpretation, and others. They make the same predictions but tell different stories about what is happening underneath. Tonight, the atoms in your body are following the patient quantum rules they have always followed. Their electrons are spread into fuzzy clouds. Their photons are flying as both waves and particles. The deepest layer of reality is quieter, stranger, and more beautiful than common sense ever suggested. Now, gently, we will look at one of the strangest manifestations of quantum behavior, the way atoms and photons can behave as both particles and waves at the same time. One of the most surprising discoveries of 20th century physics is that every quantum object behaves as both a wave and a particle. An electron, in some experiments, behaves like a tiny localized particle. In other experiments, it behaves like a spread-out wave. The same is true of photons, atoms, and even larger molecules. The wave and particle aspects are two complementary faces of one underlying reality. The most famous demonstration of wave-particle duality is the double-slit experiment. A source emits particles toward a barrier with two narrow slits and a detector behind the barrier records where each particle lands. If the particles behave purely as particles, they should pile up in two patches behind the slits. Instead, an interference pattern emerges exactly as if each particle had passed through both slits at once. The strangest version of the double-slit experiment is the single particle version. If the source is dimmed until only one particle is fired at a time, each particle still arrives at the detector as a single localized point. But over many such single particle launches, the interference pattern still slowly builds up. Each particle interferes with itself in some sense as it passes through both slits at once. If you place a detector at one of the slits to see which way each particle goes, the interference pattern immediately disappears. Knowing which slit the particle went through forces it to behave like a particle. Not knowing, leaving the alternatives open, allows it to behave like a wave. Observation itself shapes the behavior of the quantum world. Wave-particle duality applies to all kinds of matter. Electrons, neutrons, and even whole atoms have been shown to produce interference patterns in carefully designed experiments. Most surprisingly, even relatively large molecules, including buckyball molecules made of 60 carbon atoms, have been demonstrated to behave as waves under the right condition. Light shows the duality even more clearly. In some experiments, like the photoelectric effect, light arrives as discrete packets called photons, each carrying a specific quantum of energy. In other experiments, like the rainbow patterns formed by light passing through a prism or a thin film, light spreads and interferes as a wave. Both views are right. The wavelength of a quantum particle is given by a simple formula discovered by Louis de Broglie in 1923. The wavelength is equal to Planck's constant divided by the momentum. Larger particles have shorter wavelengths, which is why we do not notice the wave nature of everyday objects. A walking person has a wavelength far smaller than any measuring instrument can detect. Wave-particle duality has practical consequences. Electron microscopes use the wave nature of electrons to image very small structures because electron wavelengths are much shorter than the wavelengths of visible light. Electron microscopes can resolve much finer detail than optical ones. They have been essential to biology, materials science, and many other fields. The dual nature of matter and light is sometimes described as complementarity, a term introduced by Niels Bohr. According to complementarity, the wave and particle pictures are both true, but they cannot be observed in the same experiment. Each experiment reveals one face of the underlying reality. The two together make up the full quantum picture. Wave-particle duality also has deep philosophical implications. It suggests that the world at its deepest level is not made of the small hard objects of ancient Greek atomism, nor of pure continuous fields, but of something that is both and neither at the same time. The categories we use to think about everyday objects break down at the quantum scale. The quantum field theory, developed in the mid-20th century, resolves the duality in a beautiful way. According to quantum field theory, the fundamental entities of nature are fields that fill all of space. Particles are localized excitations or ripples in these fields. The same field can behave wave-like or particle-like, depending on how it is observed. Every kind of fundamental particle has its own quantum field. There is an electron field whose ripples are electrons, a photon field whose ripples are photons, and so on. The fields interact with one another in patient mathematical ways. The standard model of particle physics is essentially a description of how all the known fundamental fields behave together. The Higgs field, discovered in 2012 through the detection of the Higgs boson at the Large Hadron Collider, is one of these fundamental fields. The Higgs field gives mass to many of the other elementary particles. Without the Higgs field, electrons and quarks would have no rest mass, and the universe would be a very different place. Wave-particle duality is one of the strangest features of nature, and one of the most thoroughly tested. Every careful experiment has confirmed it. The world really does behave this way, even though common sense rebels against it. It is one of the ways the universe quietly reminds us how unfamiliar its deepest rules are. Today, wave-particle duality is used in many areas of science and technology. It is foundational to quantum computing, in which information is stored in quantum superpositions. It is essential to the operation of lasers and semiconductors. It is exploited in many sensitive measuring devices and in the patient ongoing work of understanding what the smallest pieces of nature really are. Tonight, every atom around you is built from particles that are also waves. The electrons in your fingertips, the photons of starlight reaching your eyes from billions of years ago, all are objects with a quiet double nature. The universe at its smallest is softer and stranger than any common idea would suggest. Now, gently, we will look at one of the most useful consequences of all this strange behavior, the way atoms emit distinct fingerprints of light, allowing us to identify them across vast cosmic distances. Every kind of atom emits and absorbs light at specific wavelengths that no other kind of atom shares. The pattern of allowed wavelengths is unique to each element, a fingerprint of light. This patient discovery has allowed us to identify the chemistry of distant stars, the atmospheres of exoplanets, and the gases of interstellar clouds without ever leaving Earth. When light from a hot source passes through a cooler gas, the gas absorbs photons at specific wavelengths. The transmitted light then shows a series of dark lines at exactly those wavelengths. These dark lines are called absorption lines, and they reveal which elements are present in the gas. The sun's light examined this way shows hundreds of absorption lines corresponding to dozens of different elements. When a gas itself is heated or excited, it can emit light at exactly those same characteristic wavelengths. This produces an emission spectrum, a series of bright lines on a dark background. Neon signs, sodium lamps, and aurora displays all show emission spectra of the gases they contain. The colors you see are signatures of specific atomic transition. Spectroscopy began in the early 1800s. The German physicist Joseph von Fraunhofer noticed dark lines crossing the spectrum of sunlight. He cataloged hundreds of them and assigned letters to the strongest ones, many of which we still use today. He did not yet know what caused the lines, but he carefully recorded them so others could investigate. In the 1850s and 60s, the chemists Robert Bunsen and Gustav Kirchhoff showed that each element produces a distinctive emission spectrum in the laboratory. They compared the pattern of solar absorption lines to laboratory spectra of different elements and identified many of the elements present in the sun. This was the beginning of astrochemistry, the study of cosmic composition through light. Helium was first discovered in the sun before it was found on Earth. In 1868, astronomers noticed an unfamiliar line in the spectrum of sunlight during a solar eclipse. They named the element after the Greek word for sun. It was nearly 30 years later that helium was finally isolated from minerals on Earth. Today, spectroscopy is one of the most powerful tools of astronomy. By splitting the light of a star into its component wavelengths, we can determine its temperature, its composition, and even how fast it is moving toward or away from us. The slow wandering of distant stars and galaxies through cosmic space is mapped by patient analysis of their light. The same techniques can be used to study the atmospheres of planets outside our solar system. When a planet passes in front of its host star, some of the starlight passes through the planet's atmosphere on its way to us. Hidden in the resulting spectrum are absorption lines that reveal what the planet's atmosphere is made of: water, methane, oxygen, and more. Spectroscopy also reveals the temperature of objects. Hotter objects emit more high-energy light. A star's color tells us its temperature. Blue stars are hot. Red stars are cool. By measuring the precise distribution of brightness across wavelengths, we can determine a star's temperature to within a few hundred degrees, even when it is thousands of light years away. Spectroscopy reveals motion through the Doppler effect. When an object moves toward us, the wavelengths of the light it emits are slightly compressed, shifting them toward the blue end of the spectrum. When it moves away, the wavelengths are stretched, shifting them toward red. By measuring the shifts of spectral lines, we can determine how fast objects are moving and in which direction. The expansion of the universe was first detected through redshifts. Edwin Hubble in the 1920s measured the spectra of many distant galaxies and found that nearly all of their light was shifted toward longer wavelengths. The further away a galaxy was, the more its light was shifted. This patient observation revealed that the universe itself is expanding. Modern spectroscopes can resolve spectral lines with extraordinary precision. They can detect lines that are millions of times finer than the ones Fraunhofer saw. They can measure the gentle rotation of distant stars by detecting subtle broadening of lines. They can detect the presence of organic molecules in the cold dust clouds between stars. Atomic spectroscopy is also used in everyday technology. The yellow light of street lamps comes from sodium atoms emitting specific lines. The red glow of neon signs comes from neon atoms. Lasers, including the ones in fiber optic communication, operate by stimulated emission of specific atomic transitions, producing pure light at a single carefully chosen wavelength. Atomic clocks, the most accurate timekeepers in the world, rely on the precise frequency of a specific atomic transition in cesium or hydrogen. The atoms vibrate billions of times per second at a frequency that is more constant than any mechanical clock could ever achieve. International time, GPS systems, and many scientific experiments depend on the patient hum of atomic transitions. The smallest features of atomic spectra reveal the deepest layers of physics. Tiny shifts in spectral lines have led to the discovery of subtle effects predicted by quantum electrodynamics. Each new generation of measuring instruments reveals new details, and each new detail tests our deepest theories with greater precision. The light of atoms is one of nature's most patient teachers. Tonight, the light from countless distant stars is still traveling toward you. Within that light, hidden in its spectrum, is information about which atoms emitted it, how hot those atoms were, and how fast they were moving. The atoms wrote their patient stories in light, and the universe has carried those stories patiently across cosmic distances. Now, gently, we will look at where the atoms themselves came from, at the patient forging of elements inside stars across the long history of the universe. Almost every atom heavier than helium in your body was once inside a star. The carbon in your cells, the oxygen in your lungs, the iron in your blood, the calcium in your bones, all were forged in the patient hearts of stars across the long history of the universe. The matter that makes you is, in a real sense, ancient cosmic ash. Right after the Big Bang, about 13.8 billion years ago, the universe was a hot, dense soup of fundamental particles. Within the first few minutes, as it cooled, the simplest atoms, hydrogen and a little helium, formed. About 75% of the original atoms were hydrogen, 25% were helium, and there were tiny traces of lithium. Almost everything else came later. As the universe continued to expand and cool, gravity gathered clouds of hydrogen and helium together. Where the gas became dense enough and hot enough, nuclear fusion began. Hydrogen nuclei collided and merged into helium. the first stars lit up. They burned for hundreds of millions of years, producing energy and slowly building heavier elements inside their cores. Stars spend most of their lives fusing hydrogen into helium. Our Sun is in this stable phase right now, and has been for about 4.5 billion years. It will continue for about 5 billion more before its hydrogen supply runs low. The energy released by this slow, patient fusion is what heats and lights every planet around every star in the universe. When a medium-mass star like the Sun runs out of hydrogen in its core, the core contracts and heats up. Helium then begins to fuse into carbon and oxygen. The outer layers expand and the star becomes a red giant. Inside the red giant, more complex elements are produced: neon, magnesium, silicon, by successive rounds of fusion in deeper, hotter layers. In stars more massive than the Sun, fusion continues all the way to iron. Iron is the heaviest element that fusion can produce while releasing energy. Beyond iron, fusion requires energy input rather than releasing it. So when a massive star builds up a core of iron, the patient fusion that has supported it for millions of years finally ends. When the iron core grows too massive to support its own weight, it collapses in a fraction of a second. The collapse triggers a supernova, one of the most powerful events in nature. The outer layers of the star are blasted into space at enormous speeds, carrying with them all the elements that fusion built up over the star's lifetime. In the extreme heat and density of a supernova, fusion continues for a brief moment, producing some elements heavier than iron: gold, silver, copper, uranium. The supernova then spreads these elements through interstellar space, where they mix with hydrogen and helium and become part of new clouds of gas and dust that will, in turn, give birth to new stars and planets. Modern astronomy has also discovered that some of the very heaviest elements, including most of the gold and platinum in the universe, are produced not by ordinary supernovae, but by collisions of neutron stars. When two of these incredibly dense stellar remnants spiral inward and merge, they release a flood of neutron-rich matter that quickly decays into heavy elements. Every atom heavier than helium in the universe traces back to one of these stellar processes: main sequence fusion, red giant nucleosynthesis, supernova explosions, or neutron star mergers. The patient pattern of which elements are common and which are rare reflects which processes most easily produce them. Iron is common because so many stars build up to iron before ending. The Earth and everything on it were formed about 4.5 billion years ago from the remnants of earlier generations of stars. Our solar system condensed out of a cloud of gas and dust that already contained traces of carbon, oxygen, iron, gold, and every other element built by earlier stellar deaths. Without those earlier generations of stars, our planet and we ourselves could not exist. The atoms in your body include some that were forged in the original Big Bang more than 13 billion years ago. The hydrogen in the water of your tears in every cell of your body is among the oldest matter in the universe. It is older than the Earth, older than the Sun, older than the solar system. It has simply been waiting all this time in different forms. Other atoms in your body were forged in stars within the last few billion years. The carbon in your cells came from the inner layers of a long dead star that became a red giant and shed its outer atmosphere into the galaxy. The oxygen you breathe was made deeper inside such a star. The iron in your blood was probably made in a supernova explosion that occurred before our solar system formed. Carl Sagan famously said that we are made of star stuff. This is literally true. Every part of you that is not hydrogen, including all of your proteins, all of your DNA, all of your skin, all of your bones, was assembled inside the cores of ancient stars and scattered across the galaxy long before our sun was born. The universe has been quietly producing the ingredients of you for a very long time. Today, stars continue this patient work. In every galaxy, fusion is producing helium and heavier elements. In every massive star nearing the end of its life, the next supernova is being prepared. In every neutron star merger, new heavy elements are being forged. The patient chemistry of the universe is still happening all the time in places far too distant to see. Tonight, somewhere in the cosmos, a star is fusing the very same kinds of nuclei that once formed the atoms in your body. The pattern continues. The patient creation of matter has never stopped. Now, gently, we will look at how the atoms forged in stars came to assemble themselves into the soft, remarkable patterns that we call life. Life is, at the bottom, a patient arrangement of atoms. Every cell of every living thing is built from a relatively small number of elements, combined into an enormous variety of intricate molecules. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, 6 elements make up nearly all of the molecules of life. A few other elements appear in smaller amounts, but are also essential. Carbon is the central element of life. A single carbon atom can form bonds with up to 4 other atoms in many possible spatial arrangements. This allows carbon to build long chains, rings, branches, and complex 3-dimensional structures. No other element has quite the same versatile chemistry, which is why carbon-based life is the only kind we have ever found. Water is the most abundant molecule in living things. About 70% of your body by mass is water. Water dissolves many other substances, transports them through tissues, regulates temperature, and participates in countless chemical reactions. It is so essential to life that scientists looking for life on other worlds usually look first for evidence of liquid water. Proteins are some of the most important biological molecules. A protein is a long chain of smaller building blocks called amino acids folded into a precise 3-dimensional shape. There are 20 common amino acids in life on Earth. Proteins serve as enzymes, structural materials, transport carriers, signaling molecules, and many other roles. Enzymes are proteins that catalyze chemical reactions. They speed up reactions by enormous factors, allowing complex chemistry to happen at body temperatures. Each enzyme is shaped to fit one specific kind of molecule, and each catalyzes one specific kind of reaction. There are tens of thousands of different enzymes in a typical living cell, all working in patient-coordinated harmony. DNA, the molecule of heredity, is a long double helix made of just 4 kinds of building blocks called nucleotides. The order of nucleotides along the strand carries the genetic information of the organism. A typical human cell contains about 3 billion nucleotides of DNA, coiled and packed into a nucleus only a few millionths of a meter across. The 4 nucleotides of DNA, adenine, thymine, cytosine, and guanine, pair with each other in a specific way. Adenine pairs with thymine, and cytosine pairs with guanine. The pairings are held together by gentle hydrogen bonds. This pairing rule is what allows DNA to copy itself by splitting the two strands apart and using each half as a template to assemble a new partner. Cells use the genetic information in their DNA to make proteins. The DNA is first transcribed into a related molecule called messenger RNA, which travels to a cellular machine called a ribosome. The ribosome reads the RNA in groups of 3 nucleotides and uses the information to assemble a protein, 1 amino acid at a time, in the exact order specified. Carbohydrates and fats provide energy for life. Carbohydrates, like sugars and starches, are chains of carbon-rich molecules that can be broken down to release energy. Fats are even more energy-dense. Both are built from familiar atoms, mostly carbon, hydrogen, and oxygen, assembled into different patient patterns. Cell membranes. The boundaries that separate the inside of every cell from the outside are made primarily of lipid molecules called phospholipids. Each phospholipid has a water-loving head and a water-repelling tail. In water, these molecules spontaneously arrange themselves into thin double sheets, with the heads facing outward and the tails turned inward, forming a flexible barrier. Iron is essential for carrying oxygen in your blood. The protein hemoglobin contains 4 iron atoms, each of which can grab 1 oxygen molecule and release it where it is needed. Without iron, oxygen could not be efficiently delivered from your lungs to your tissues. Each red blood cell contains hundreds of millions of hemoglobin molecules, gently shuttling oxygen back and forth. Calcium is essential for bones. Calcium atoms bonded with phosphate ions form the hard mineral hydroxyapatite that makes up most of bone. The same mineral in a slightly different form makes the shells of marine creatures. Calcium ions are also essential for muscle contraction and for signaling between cells. Sodium and potassium are essential for nerve signaling. Each neuron in your brain maintains an electrical voltage across its membrane by carefully controlling the flow of sodium and potassium ions. When a nerve fires, the voltage briefly reverses, then resets. The patient-orchestrated motion of these simple ions is what produces every thought you have ever had. Atoms in living things constantly turn over. The atoms in your body today are not exactly the same as the atoms in your body a year ago. Through eating, drinking, breathing, and excreting, you constantly exchange atoms with your environment. The form of you persists, but the atoms that make up that form are slowly replaced. You are, in a real sense, a pattern, not a substance. Despite this constant turnover, your identity remains stable. The pattern that is you, your shape, your memories, the way your cells are organized, persists even as the atoms themselves change. Life is the slow, patient maintenance of pattern through the patient flow of matter. You are a process more than you are an object. Tonight, somewhere inside you, billions of biochemical reactions are happening every second. Enzymes are gently working. Proteins are being folded and unfolded. DNA is being read. Membranes are quietly maintaining themselves. Atoms forged in long-ago stars are being arranged into the patient pattern that is the living you. Now gently we will look beyond living things and consider how atoms are present in everything around us, in the air, in the ground, in every object we touch. Atoms are everywhere. The chair you are sitting on is made of atoms. The air around you is made of atoms. The ground beneath your feet is made of atoms. The light reaching your eyes from the screen or page is photons, emitted by atoms and detected by atoms in the cells of your retina. Every object and every signal in the world around you is mediated by atoms. Solids hold their shape because their atoms are arranged in patient, orderly patterns or in rigid, disordered networks. In a crystalline solid like a diamond or a salt grain, the atoms occupy fixed positions in a repeating lattice. In an amorphous solid like glass, the atoms are still locked in place but in a more random arrangement. In both cases, the atoms vibrate gently in place but do not flow. Liquids are made of atoms or molecules that are close together but free to slide past one another. The atoms are still touching their neighbors, but the neighbors are constantly changing. This is why liquids flow to fill any container while solids hold a fixed shape. Water, oil, and molten metal are all examples of liquids. Gases are made of atoms or molecules that are widely separated and moving freely. The molecules in air, for example, are roughly 10 times farther apart than they would be in a liquid. They fly through space at hundreds of meters per second, occasionally colliding with each other. The pressure of air is the gentle, constant patter of countless molecules striking surfaces. Plasma is sometimes called the fourth state of matter. In a plasma, the atoms have been heated so much that some of their electrons are stripped away, leaving a soup of positive ions and free electrons. Stars, lightning, fluorescent tubes, and certain types of welding all involve plasma. Most of the visible matter in the universe is actually plasma, since most of it is inside stars. The air in any room contains an extraordinary number of atoms. A single breath inhales roughly 25 sextillion molecules. Most are nitrogen, 21% are oxygen, 1% is argon, and tiny fractions are carbon dioxide, water vapor, and other trace gases. Every breath is a brief patient meeting with countless invisible atoms. Soil is a complex mixture of mineral grains, water, air, and biological material. The mineral grains are mostly oxygen, silicon, aluminum, and iron, arranged in different mineral crystals. Mixed with the minerals are organic carbon compounds from decayed plants and animals, providing the nutrients that new plants need to grow. Soil is one of the most chemically complex substances on Earth. Rocks are aggregates of mineral crystals formed under various conditions of heat and pressure inside the Earth. Granite contains crystals of quartz, feldspar, and mica. Limestone is mostly calcium carbonate. Basalt is solidified lava rich in iron and magnesium. The patient slow chemistry of how rocks form has shaped the surface of our planet over billions of years. Metals are made of densely packed atoms with a sea of shared electrons. The flexibility of this shared electron sea is what makes metals conductive, shiny, and malleable. Steel is iron alloyed with small amounts of carbon and other elements, which alters its properties in useful ways. Aluminum is much lighter than steel and resists corrosion because its surface forms a stable oxide layer. Glass is an unusual solid in which the atoms are arranged in a random rather than crystalline pattern. Most ordinary glass is a mix of silicon, oxygen, sodium, and calcium. The random arrangement is what makes glass transparent to visible light. There are no regular crystal planes to scatter the light. Glass has been used by humans for thousands of years. Plastics are long chains of carbon-based molecules called polymers. The carbon backbone can carry many side groups, which determine the plastic's properties: flexibility, color, strength, melting point. Some plastics are made by chains of identical units repeating many thousands of times. Others have varied sequences that give them complex behavior. Almost every plastic was unknown to humans a century ago. The atoms in everything around you are constantly vibrating. In a solid, the vibration is small and confined. In a liquid, the atoms vibrate while sliding past each other. In a gas, the vibration is high-speed motion through open space. Temperature is, deep down, a measure of how vigorously the atoms in a substance are moving. The hotter something is, the faster its atoms are moving. Heat flows from warm objects to cold ones because vibrating atoms collide with their neighbors. The faster moving atoms transfer some of their motion to their slower moving neighbors, slowing themselves while speeding up the others. Over time, the system reaches an average, a gentle, steady warmth shared by all atoms involved. The patient mixing of motion is the deep basis of thermodynamics. Even the patient stars in the night sky are reachable through atoms. The light from a distant star reaches your eye as photons. Those photons interact with atoms in the retina of your eye. The atoms send signals along nerves built from atoms to a brain built from atoms. The act of looking at a star is, at every step, a quiet conversation between atoms. Everything you have ever loved or feared, everything you have ever held or seen, every memory in your head, every thought passing through your mind right now, everyone is mediated somewhere by atoms. Atoms are the universal currency of existence. They are the patient, quiet pieces from which all of experience is built. Tonight, as you rest, the atoms around you are still vibrating, still bonding, still emitting and absorbing light. They have been doing this for billions of years. They will continue for billions more. They are absolutely indifferent to time and absolutely patient. The smallest pieces of the universe hold everything else in place. Now gently, we will bring our journey through the atom to a soft close, returning slowly to the quiet of sleep. Thank you for staying with us this long. If sleep is closer now than it was when we began, then this night did its work. Subscribing helps us return next week with another slow journey through the quiet world of the atom, recorded with the same patient voice you have been listening to tonight. Good night from all of us at the Circadian Institute. We hope sleep is finding you. Atoms are still quietly humming through every molecule of air around you tonight. Electrons are still tracing their patient quantum clouds. Photons are still being absorbed and released. Nuclei are still holding their dense, bright cores together exactly as they have for billions of years. And with that, we bring tonight's quiet journey through the world of the atom to a soft close. The electrons are still in their patient orbitals. The nuclei are still being held together. The atoms in every corner of you and the universe are still doing exactly what they have always done. They will all continue without us. Sleep softly tonight.